virtual meetings. I'll be talking about work done in collaboration with Eduardo Casali, who is based in Davis, and Sebastian Misera from the Institute of Advanced Studies. And this is work, this is ongoing work that we started putting out last year on the archive. So here's a short outline for the talk. I'll give some motivations of explain what we're doing and why we're doing it. Then I'll come to this twisted homology formalism. It should remain low tech all over the talk. So I'll do my best for this. Then I'll come to applications to string theory, and I'll explain how this formalism allows you to get the monodromies, which I'll explain what they are. And then also that one of the main applications is getting a minimal basis of string loop integrands. So I'll also explain what this means. Right, so I'll start out with two type of quick introductions. The first one is an explanation of the figure, of the drawings, that there will be a ton of them in this talk. So I'll just want that everybody is on the same page. So the first thing is that string scattering amplitudes, they correspond to Riemann surfaces. So when you'll see something like this big blob sphere with 4 points, it corresponds to a 4-point scattering in closed string theory. And physically that object encompasses the field theory results and a bunch of alpha prime corrections. So alpha prime is the length of the string squared. So it's like correction that vanish when the string is very small. Right, so that's one thing. Also, I say Riemann surfaces. So when it's closed string, it's Riemann surfaces without boundaries. And when it's open string, it's sort of disks like that. The figures look like one another, but hopefully there shouldn't be confusion. And finally, the loop expansion in string theory is done by the genus. The number of holes is the genus, and it's the number of loops of the corresponding graph. So that's one thing. Then maybe, I don't know if the slide is useful or not. So if you want some actual expressions to be able to tune in this talk, so here is the sort of objects we'll be dealing with. So that's a string amplitude at genus G. So it's a G loop thing. First off, we'll be doing integrand. So there is a loop momentum integration in front of it. Then you have some sort of moduli space measure for the moduli space of Riemann surfaces that we will not be concerned with in this talk. And then you have the endpoints that like hover around on this Riemann surface. You need to integrate them on the surface sigma G. And then there's this expression. This I'm not mentioning at all. And this is the prime form. This is the thing that will give most of the monodromies. And at genus 1, I'm also mentioning this to justify my participation to this conference, because at genus 1, you have those elliptic functions in there. So this object here is a ratio of, sorry, there's a typo here, is there isn't a typo, that's the expression, sorry. And there's similar expressions at genus G. So in case you needed an actual formula to start tuning in, here it was, but now we'll mostly forget about it for quite some time. So some general comments. First off, why are we doing this? Because it turns out that string amplitudes are extremely rich objects, and working to understand their structure has proven in the past to be a very fruitful operation that outsourced many results in many different directions. And one of the reasons why the strings have such a nice structure is because they have two different expansion. One of them is the loop expansion, like in field theory, and the other one is this alpha prime expansion, which, by the way, is also in some sense another loop expansion, but on the wall sheet on this surface, if you have a quantum field theory on the surface. So you have sort of two loop expansions that are intertwined, and they're intertwined by the fact that you have some conformal symmetry and modular invariance on the surface. And that creates very tractable expressions that are nice and that have lots of symmetries. And there's also some more generic things of string theory, that there's the supersymmetry and a bunch of dualities that constrain the expressions to assume nice and unique forms sometimes. So for these reasons, for this sort of double expansion, you can really play around with those integrals, and they turn out to appear in other contexts. There's no surprise that they appear in Feynman integral context, because you have the Feynman integrals within this thing. And the alpha prime expansion also has some flavor of a Feynman integral. So I'm not going to be Federico discussed this direction, the downward direction, yesterday. I'm mostly going to be describing the horizontal direction in this talk. So here's a quick summary, quick pitch, and a recall of history. So the monodromy relations in string theory, they are a set of linear relationship between string tree amplitudes or loop integrands. I'll come to this afterwards. And they relate different type of graphs and topologies of graphs. At tree level, they've been known for a long time, since Platé, which I forgot to cite on this slide, in the 70s. And then Pierre Vanov, Emile Bjornborg, and Paul Langard, and then Stefan Stieberger worked out these things in full generality. Then it was sort of recently extended to loops by these authors. And what we did with Eduardo and Sebastian is to recast this whole program in the language of twisted homology that had the effect of, well, first off, it's a very robust framework. So it allows to compute these monodromies extremely accurately, and you don't have to wonder about combinatorial factors and all sorts of things. It's very streamlined, the computation in this framework. Second, it's a complete formalism. It gives you like it gives you a minimal basis. This set of linear relationship between the string integrands, it tells you that they're not all independent. So there's a minimal number of them, and this twisted homology formalism gives you a way to compute this minimal basis at loop order. And the second application is this KLT, Kawai-Lewis-Lentai framework that Federico mentioned yesterday. It's pictorially how you glue open string amplitude to closed string amplitudes. And that has been done for a long time at tree level, but at loop level, there isn't really a working KLT formula. So we would like to uncover this. And that connects, for the experts, that connects to this color kinematics duality program in field theory of Bern and friends. Okay, so that was the one slide pitch. And there's also one comment I want to make, which is that one of the reasons why I was particularly interested, and I still am, in this KLT framework is that, for those of you who have heard of this ambitwistor string and scattering equation program, in my opinion, having a KLT formula is the only way to go beyond what's been done so far and to really understand this formalism. That's just a quick comment. I'm not explaining what these things are. So now let's come to string amplitude and twisted homology, unless there's a question. Right, so here is one amplitude, a famous one. It's the Veneziano amplitude for open string tachyon scattering. It's an integral from 0 to 1 of this complex variable z. Alpha 0 of x is just 1 plus alpha prime x, and s and t are the usual kinematic invariant. S is the center of mass energy, and t is the momentum transfer squared. Of course, you'd recognize immediately a beta function here, so it's a ratio of gamma functions. And to get the actual Veneziano amplitude, you need to sum over the other crossed channels. But that's the object we will be looking at right now. And the crucial feature is that it's a multi-valued function. It has cuts all over the place, from z and from 0 and from 1. So to investigate this multi-valuedness, we're gonna simplify the problem and just look at one bit of the integral, and we get rid of all this alpha prime and signs and everything. We look at this function z to the s, where s is some rational, not rational, real number. So that defines an infinitely sheeted Riemann surface that's drawn here, and we take a cut along the negative real axis here. And the question is, Now let's consider this path gamma that goes through this cut, red dash cut. What's the meaning that we want to give to this, to integrating z to the s through this cut in this way? So first off, let me draw this on the plane. So that's what it is. The contour gamma has 4 individual bits. And the one thing that we would like this integral to mean is that at least it's homotopy invariant. Like it should not depend on x, for instance. You should be able to move x here or back here. The integral should have the same value. So here is one way to have a homotopy invariant expression. We close up the contours by this gamma u and gamma d, gamma up and gamma down pieces here. And we look at this expression, we split it in 2 pieces. So both of these guys, sorry, the second term here vanish because there's no pole inside nothing, so it's just 0. So it would seem like you have a homotopy invariant expression, but somehow it's not quite the right way to do this because this gamma u and gamma d pieces, they don't really cancel in the way you would want them to. So we're going to use the fact that we know how to relate the gamma u and gamma d integrals because it's just this z to the s function. So we know that from either side of the cut, it varies just by this e to the 2 pi I s constant number. That's the monodromy factor. So if we instead define our integral I in this way, where we now add this extra bit, this extra phase, these 2 gamma u and gamma d thing cancel out. And we remain with this integration, the integration over gamma 1, some phase factor integration of gamma 2, phase factor gamma 2 prime, and just you lose the phase factor when you cross back the cut. And in this way, it's obvious that the integral is still homotopy invariant. So that's the rule to how to do for how to do integration through cuts. I'm sorry if it was too obvious or I spent too much time, but it's actually just a way to get going with the following. So this rule motivates the definition of a twisted boundary operator. So which acts in the following way. If you consider this path gamma that goes through a cut with this monodromy factor alpha, which should not be confused with alpha prime. I'm sorry, it's just the variable we used for these things. The boundary of, when you apply this boundary operator on your one-dimensional chain gamma, you pick a b times the monodromy factor alpha, b is the point, minus a. The plus sign for b is because you arrive on b, and the minus sign on a because you leave from a. So that defines a twisted boundary operator. And now that you have your boundary operator, you can go ahead and define your homologies like that by demanding that cycles are chains modulo exact cycles. So you want a cycle. A cycle is a chain whose boundary is empty in the twisted homology. So that's not a cycle, right? Because the boundary isn't empty. However, if you remove, no, sorry, even if you remove sorry, forget my comment. So that gamma thing here is not a twisted cycle. I'm just gonna mention a few examples of twisted cycles, but it would be more relevant for the intersection business, which I'm not gonna allude to really in this talk. So let's consider this little drawing here. Now we have 2 cuts, alpha I with monodromy alpha I and alpha I plus 1, for instance. These points zi and zi plus 1, they're removed from the surface. They're marked points. And we first consider the path gamma, the green path. So it's rho I plus rho I plus 1. AI and AI plus 1 are the intersection at these little points here. The boundary of gamma is just easy to compute. It doesn't cross any cut, so there's no monodromy factor involved. It's just the boundary of this first bit, which is plus AI. Zi is not in the boundary because it's not in the surface, so it doesn't, it's removed from the surface. Then you do for rho and you do for this bit, and you find that the boundary is empty. That is a twisted cycle. Turns out, now you could define another one that's related to this Pochammer symbol, Pochammer contour framework, which now would go through this cut. So it starts from a little bit below here, goes around, crosses the cut, continues like that, goes above, crosses the cut again, and ends up here. You'd need, so you have this gamma I part, rho, and gamma I plus 1. If you apply this rule I've told you about before, you would need to define your path gamma tilde with inverse monodromy factors so that it is a cycle. But then when you compute the boundary of this cycle, you'd find it's empty, so it's actually a cycle. And it's relevant for the intersection theory business because it's kind of easy to see the intersection between this straight cycle here and this blue cycle, because the cycles actually intersect and they just turn out to be homologous. And so the intersection would be given by the value. So if the two cycles intersect, gamma I and rho I would intersect, and you would keep this phase factor. But we could discuss this tomorrow if you wanted to have, or maybe Sebastian would allude to this. So now back to the monodromies. The monodromy relations in string theory, they correspond to vanishing of boundary twisted cycles. And let me illustrate what this means in this example of the 4-point Veneziano amplitude. So here is the amplitude that we talked about before. And we're going to define this function T of Z, which is the one that encodes, that knows everything about the monodromies when you loop around 0 and 1, right? So we're now going to look at another integral, not the original one, but a tilted one, which is almost the same, apart from the fact that we integrate this function T of Z. But since we're still integrating between 0 and 1, this guy, now you need to pick the side on a branch. So depending on if you're above the real axis or below the real axis, it will be plus or minus I pi t. So this is how these two integrals are related. And we're gonna play with this guy now. First off, just a quick comment. So this would be the 3 different orderings that I'm going to describe just after. The ST channel corresponds to 1, 2, 3, 4, SU to 1, 3, 4, 2, and this one to the other ordering. ST and U are those kinematic invariant. They sum up to the sum of the squared masses of the incoming particles, 1, 2, 3, 4. And in our example, now they're going to sum to 0. We're going to take a look at the massless scattering. So we go back to our tilted integral, and we replace it by a closed contour integral, which is going to vanish. So what contour integral is this? Well, we have 2 of them. It could be either the plus integral here on the positive part of the real axis. It closes off at infinity, but the contour drops off. So it's just really a line integral. And you have the minus integral. I've figured here the monodromies you get when crossing those cuts. Now we have 3 of them, but since S plus T plus U sums to 0, they're not all independent, they're related. That's why S is the sum of T and U, channel monodromies, sorry, the product. So, and just to represent what these guys are, I've drawn the same picture, but on the real axis being compactified to this circle. the plus contour is the one that goes through the cuts, then the minus contour is the one that doesn't go through the cuts, okay? And on each of these bits of the contour, the leg 1, which was our particle, sorry, I forgot to mention this. Okay, let me step back for a second. I forgot to mention this point. So this particle Z1, this complex variable Z corresponds to the position of the particle number 1. It could be any other, but due to conformal symmetry on the disk, you have 4 points, 4 particles, 1, 2, 3, 4. You can fix the positions of 3 of this particle. Particle number 2 is fixed at 0, particle number 4 is fixed at 1, and particle number 3 is fixed at infinity. It's our particle Z that was originally being integrated between 0 and 1. It's our Z1. Now when we integrate it along the whole real axis, our particle 1 is integrated everywhere here. So it corresponds to 1 being inserted between 2 and 4. That's our original starting point. 1 being inserted between 4 and 3, and 1 being inserted between 3 and 2. So you recover the 3 different channels I mentioned before, ST, TU, and SU. And so what do the monodromies tell you? Well, they tell you that on the plus axis, you will, well, okay, so I wrote this to be completely rigorous. It turns out that it's only the TU written in this way. The TU amplitude here corresponds to that integral. And in here, Z is bigger than 0 and Z is bigger than 1. So it doesn't have a monodromy phase. So it's like if we started from here. Then on the SU part, you cross U, the U monodromy, and you go from infinity to 0, or minus infinity to 0. So you pick up just this monodromy here. And on the ST part, when Z goes between 0 and 1 again, you keep this monodromy and you pick up the S monodromy in addition. So that explains those phases. And now on the minus axis, well, there's no cut, so you pick up nothing. So the first thing to observe is that instead of 3 independent integrals, because you have 2 relations between them, you have only 1 independent integral. So, right, so, yes, sorry. So you may wonder why they look so asymmetrical. One of them is just the sum and the other one has these funny factors. It turns out that it's just related to this tilde versus non-tilde thing. I told you that, right, if you remember, because we relaxed that absolute value condition, we picked up a half phase like that, I pi, plus minus I pi. These guys were 2 I pi's. So when you combine the I pi plus minus I pi and the 2 I pi, you get these phases. And in the field theory limits, so this is the relations. They were found by Platé in 71, and they generalized to endpoints, as I'm about to mention. Just to give a bit of intuition about these relations, in the field theory limit, they give 2 independent relations again. Ft is subscript for field theory. One of them is this Kleist-Coif relation, that the sum of the amplitudes vanishes, and the other one is this BCJ relation, Bern-Carrasco-Johansson relation. It's kind of a remarkable expression that goes beyond crossing. Crossing would be just ST symmetric. Now you can exchange S and T through this Finney mechanism. So it's an interesting relation. And the point is that these relations, they generalize to endpoints. Now you look at the generalization of our integrand before. Again, you do the same business as looking at what happens for the particle Z1. So this is the relevant part of the integrand. again, because this was agnostic about the ordering of these particles. Now this isn't, so this will pick this will pick phases when you want to relate integrals of t to the actual integral. Then you have all of the phases coming from the monodromies, and you obtain similar type of relations by doing the same thing as I have explained just before. So the point is that, again, the vanishing along the plus and minus contours will reduce the total number of integrals from n-1 to n-3. And let's have a look quickly at this reduction, because it's at the basis of the total number of independent integrals. You know that from the perspective of the variable z1, there is only n-3 different integrations. And the point is that you can do this iteratively. There's a vibration structure to the moduli space, and I refer to Sebastian's paper for a longer intro to this whole set of ideas. But schematically, this picture is kind of reproduced from Sebastian's paper, by the way. So schematically, the idea is the following: when you work at 4 points, you realize that instead of 3 independent integrals, you have only 1. And then on top of these 4 points, you look at point number 5. And likewise, you realize that instead of 4 integrals, you have 2, etc. And this vibration structure will give you that you should just do the product and you find n-3 factorial independent integrals. And we'll come back to this vibration structure afterwards when we do loops, which is now. So the setup, this would be an open string amplitude with a bunch of marked points inside and outside. So it's like a non-planar amplitude. You would again draw this little dashed line, which corresponds to the cuts. But there's one important thing that I want to comment on right now, which is the following. So we've been essentially doing Cauchy's theorem before. And to do this, you need to have holomorphic functions, but it's a theorem that on the torus or any Riemann surface, you wouldn't have, there isn't holomorphic functions that are periodic in both directions, so that are double periodic on the torus, which means that the function is at the same time holomorphic and invariant under z to z plus tau and z to z plus 1. I'm sorry, I meant meromorphic. Your functions need to have one single pole, and by this reasoning, you would show that their single pole, the residue of the single pole, need to be 0. So one way out of this is to relax. So the thing is that the integral, the string amplitudes, they're not integrals of holomorphic functions. You have im z entering, as you've seen in Federico's slides yesterday. And one way out of this to restore holomorphy of your integrand is to go to this chiral splitting formalism, which introduces explicitly variables that in field theory are loop momentum. So this breaks the double periodicity, but guarantees that your integrand is now holomorphic, so you can apply Cauchy's theorem. And this little drawing here explains really rapidly the idea, but we figured with Oliver that maybe it would be better to explain it in a longer way tomorrow morning during the discussion. So let me just explain quickly what's happening here. So it's like a bit of a Riemann surface of genus G, and you have those A cycles here. So that's one A cycle. I've drawn this arrow and L mu, so that's our loop momentum. Mu is the spacetime Minkowski index. So that L mu is the momentum flowing through this disk. It's the flux of momentum flowing through this circle. And one of the properties is that when one puncture Zi goes through the circle, the loop momentum jumps. So you've lost the double periodicity, but the integrands are holomorphic. So you will be able to run the same Cauchy theorem business. More tomorrow if interested. So what this means is that in our annulus, we need to introduce a cut along which we will be able to integrate, but the value of the function on either side of the cut is not going to be the same. That's going to introduce some extra monodromies, some global monodromies, which will depend on the loop momentum. And that's why the relations are going to be loop integrand relation and not amplitude relation. So this is a slide to just say a few of the advantages of reasoning in this way. Firstly, because these monodromies were worked out by Pierre and me and by Stefan Stieberger and Stefan Hohenegger by hand in 2016, 17. The advantage of going to the twisted homology formalism, one of the main advantages that I found is that you can count the exact number of independent cycles. When you work out the monodromies by hand, you know that they're relations, but you do not know what's the minimal number, what's the size of the independent building blocks of that are in these relations, unless you work out the rank of the matrix that correspond to these relations. With the twisted homology business, you're guaranteed by mathematical theorems behind it that you can count the number of cycles via Euler characteristic computation. So, and that computation is easy to do. So you know that when you've built sufficiently many cycles, you have a basis because you've reached the correct number. And it's also important to have a basis because of the KLT ideas. If you want to build a bilinear form of open string amplitude to obtain a closed string amplitude, you need to use elements of a basis. And this twisted homology formalism gives you those elements. So what are those cycles? And let me describe our setup first. So we don't really work on annuli, and that's an important point for later. We work on double covers. So here is a picture of a torus, it's a donut, and it's intersected by this green plane along this external boundary. On the internal boundary, you can think of this guy as being our B cycle. And the upper part and the lower part, they give two different annuli here and there. The A cycle is a combination of two cycles. There's the upper one on this cycle and the lower one with prime and double prime superscripts. And the punctures, they lie on either sides, either boundaries of our annuli, on the B and on the D cycles. So now that connects to this image, the punctures lie inside on B and outside on D. And just to be definite, that's what it looks like. So we have our annulus, we have our torus. It's a fundamental domain of the torus, goes from -1/2 to +1/2. And the height is given by the modular parameter. It needs to be, in general, this guy tau can be complex, but for the both annuli to be copies of each other, it needs to be purely imaginary. So the A prime cycle is up here and down here because it differs by, it's just shifting by B cycle. Same for double prime. D is this guy, and B is, sorry, those two B cycles are one and the same. They're this orange cycle. They are identified. So that's why the punctures here are in the same position, because they're just the same thing. And you're free to choose how you put your branch cuts again. So just like before, we had branch cuts going above and not below. You can do the same here. They go in one quadrant and not the other. But hopefully it should be apparent that we're just doing exactly the same thing, except that now we're representing things vertically instead of horizontally. And let's look at this 4-point example. What this green line here is supposed to represent the position of Z1 that is being traveled around the annulus on both sides, right? 2, 3, and 4 are fixed. We're doing a 4-point amplitude. and we travel the position of Z1 everywhere. The only way to do this is to have this closed contour and extend it so that it touches all 4 boundaries of each quadrant. So let's just look at one portion. And I've represented the topologies, the various topologies that this correspond to. On this bit here between z equals 0 and z equal whatever is z2 at, this is this topology. Likewise, when 1 is between 2 and 3, we have this topology, and etc. I've represented 4 here, but just because it doesn't, I mean, it's on the same boundary, it's just one and the same thing. Then on this boundary at z equal, real part of z equal a half, you have one that's inside, so it's a non-planar topology. And here is our new important ingredient. It's a phase. Sorry, this alpha are just the monodromies that we had before. They're the same, but now we have a new phase that depends on the loop momentum. I'm not explaining the shape of it, but essentially it corresponds to the fact that you're doing this shift, z goes to z plus a half. You're switching boundary, and that introduces a global monodromy that wasn't present at tree level. It's a new ingredient at loop level, and somehow it has to be there because of this holomorphy versus double periodicity clash. So that phase now depends on the loop momentum, and that's why you can't pull it outside of the loop momentum integration. It needs to stay inside the loop integration, and that's why the relation just are just between integrands and not amplitudes. Okay, so that's for this external guy. Now you have 2 new bits of the contour, where one is on top here and one is below here. And if you don't integrate all the loop momentum, there's nothing you can do there here. These bits of the contour are always there. And just a comment, that's one point where Stefan Stieberger and Stefan Hohenegger and Pierre and me disagreed on. So firstly, in the for planar topologies where all the particles 2, 3, blah, 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 n are on one side, you can indeed remove these extra new graphs by integrating the loop momentum. But in general, where the particles are on either side of the boundaries, these guys cannot be removed because they have phases, and Stefan Stieberger and Stefan Hohenegger got these phases correct, and we got them wrong at first with Pierre, which led us to believe that if you integrate all the loop momentum, this guy would disappear. That's not the case. We found the same mistake, and indeed we agree with Stefan Stieberger and Hohenegger on this point. But so that's about what happens if you try to integrate out the loop momentum. At the level of, if the loop momentum is there was never a question. These graphs are always there. And there are new sort of physical elements. You don't really expect them from the open string perspective. The particles are never inside the bulk. They're always on the boundary. So that's something that is new. And in terms of equations, you would obtain things that relate these 3, 1, 2, 3 planar contribution and this non-planar guy, and these 2 extra up and down contours. And somehow I've been keeping track of time on my phone, but I'm just realizing that it's not an hour, it's 45 minutes. So I'm gonna conclude in 2 minutes. In case you're wondering, these guys, they're connected to this BCJ duality, and this is what we discussed in our last paper. I'm not commenting really more on this. The setup is similar at higher loops. You need to cut the surface with this external D cycle, and you have your B guys inside. You can find your, I wouldn't have commented long anyway on these figures. You define your branches in the same way, and you have 2 relations that, again, decrease the number of independent integrands. And now you want to build your cycles. So you do it in the same way as we did at tree level. You want to use this vibration operation. So you fix one point up there, point number 1, and then you integrate point number 2 everywhere. it can be anywhere, right? Let's pick it on top, but it could have been on the side or on the bottom. Then you do the same for point number 3, and it can be anywhere again. So you iterate the process, and at the end, your cycles are just these blue lines, and you remark that they need to go above, and they need to do this sort of angular parts here. So that these contours are physical, and they must be important in the context of KLT. I'm raising this because I think it's interesting. It's important that people thinking about KLT are aware of that. You can compute a minimal number of amplitudes. I'm not commenting on that right now. And to conclude, I hope I gave a good flavor of why twisted homology is a good formalism to think about these integrals. One of the big applications is going to KLT formula. And not commenting on the last point. And thank you.
Thank you. Let us take a couple of seconds to unmute ourselves. Great, so we have some minutes for some questions, if there's any. Okay, maybe in, okay, I don't see any questions in the chat, or are there any raised hands? Is there anyone who's struggling with the Zoom features and wants to speak up? Okay, then maybe in view of time, we proceed with the next talk, and then we have more time for questions also after the next talk, and of course tomorrow morning in the discussion.